Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine this. You're floating in silence, light years from Earth, surrounded by the black canvas of space, each pinpoint of starlight, a sun in its own right, each one a potential harbor for life. Suddenly, a single star flickers in a peculiar way. Not because it's dying, not because it's erupting in a violent flare, but because a planet has passed in front of it. Now imagine this. Light from that distant sun filters through the thin veil of a planet's atmosphere, carrying, with it, a secret, the spectral signature of organic molecules. That's not just poetic science fiction anymore. It's real. In a groundbreaking achievement, astronomers have, for the first time in human history, discovered organic molecules in the atmosphere of an exoplanet. And that moment could be the first true clue that we are not alone. This is more than just a distant measurement. It's a crack in the cosmic mirror we've been staring into for centuries. A signal, a fingerprint, a hint that the chemistry of life might not be unique to Earth, but rather a universal trait of planets forming around stars across the Milky Way. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. Let's begin with the subject of this interstellar revelation, an exoplanet called WASP-39b. This strange world lies about 450 light-years away in the constellation Virgo, orbiting a star not unlike our Sun. But unlike Earth, WASP-39b is nothing like a cozy home for life. It's a hot Jupiter, a massive gas giant that orbits dangerously close to its star, completing one orbit in just 4.4 days. Because of this extreme proximity, the planet is constantly scorched by stellar radiation, with daytime temperatures soaring to nearly 1,600 degrees Celsius, hot enough to melt lead. ASP-39b is over 1.3 times the radius of Jupiter, but only about 1/4 the density, making it an especially puffy planet with a thick extended atmosphere. And that puffiness, believe it or not, is exactly what makes it scientifically precious. Its bloated atmosphere provides a large canvas for astronomers to study, and when this exoplanet transits, or passes in front of, its host star, some of the star's light travels through the planet's atmosphere before reaching us. This light carries vital information. It's been altered by the gases floating in those alien skies. Through this method, known as transmission spectroscopy, astronomers can break down the light into its component wavelengths to determine which chemicals are present. Enter the James Webb Space Telescope, or JWST. With its 21-foot gold-coated mirror and highly sensitive infrared detectors, JWST is the most advanced observatory ever placed in space. Designed to look back into the early universe and decode planetary atmospheres, its instruments are capable of capturing minuscule changes in starlight as a planet transits. In the case of WASP-39b, JWST's near-infrared spectrograph and mid-infrared instrument collected data from 4 separate transits. Scanning a wide range of infrared wavelengths, the data was a treasure trove. It revealed not only previously detected molecules like water vapor, carbon dioxide, and carbon monoxide, but for the first time ever on an exoplanet, methyl chloride and hydrogen cyanide. These are not just any gases. Methyl chloride, also known as chloromethane, is an organic compound that here on Earth is produced both naturally and biologically by certain types of plankton, fungi, and plants. Hydrogen cyanide is another organic molecule, and though it's toxic to humans, it's essential in the prebiotic chemical pathways that scientists believe may have led to the formation of life on early Earth. Let's pause there. Think about that for a moment. These are the same kinds of molecules that, billions of years ago, danced through Earth's primeval skies, perhaps laying the foundation for the emergence of life. Now, we're detecting their signatures on a planet hundreds of trillions of kilometers away, a place we cannot see directly with our eyes, a place that until recently existed only as a slight dip in a star's brightness. And yet, through the combined power of physics, engineering, and sheer curiosity, we're peering into its atmosphere and pulling out molecules that hint at the same chemical processes that helped build us. The implications are staggering. This discovery doesn't mean there's life on WASP-39b. It's far too hot for that. But it does mean the chemical ingredients for life may not be confined to just our little corner of the universe. These organic molecules may be far more common than we previously believed. In fact, their presence on such a hostile planet raises tantalizing questions. If these complex molecules can survive in such harsh environments, what might be possible on cooler, rocky exoplanets orbiting in the habitable zones of their stars? The detection itself is a technological marvel. Scientists had to isolate the planet's faint spectral signal from the overwhelming glare of the star. Even minute shifts in light intensity, on the order of 1 part in 10,000, had to be measured with razor-sharp precision. Then, through complex atmospheric models and Bayesian statistical analysis, they tested thousands of combinations of possible atmospheric compositions until the models matched the observed spectra. The presence of CH3Cl and HCN stood out not as guesses, but as statistically significant features. But these signals don't just tell us what's present, they also hint at how the planet's atmosphere might be behaving. For instance, the presence of both methyl chloride and hydrogen cyanide suggests dynamic chemistry involving carbon, hydrogen, chlorine, and nitrogen, elements central to organic molecules. These compounds may be forming deep within the planet and being transported upward, or they might result from the breakdown of even more complex chemicals under intense ultraviolet radiation. It's here that the philosophical weight of the discovery starts to settle in. For the first time, we're seeing not just planets, not just atmospheres, but organic chemistry out there on another world, the same type of chemistry that led eventually to life on Earth. The cosmos, it seems, may not just be a cold and lifeless void, it may be chemically active, diverse, and fertile. And this is just the beginning. The JWST team is already setting its sights on other exoplanets with more Earth-like temperatures. If organic molecules can be detected on a superheated gas giant, what might we find on temperate, rocky planets like TRAPPIST-1e or LHS-475b? Let's travel deeper now, not just through space, but through time and meaning. Because to understand the weight of this discovery, we have to rewind the cosmic clock, all the way back to Earth's own beginning. Picture it. Over 4 billion years ago, Earth wasn't blue and peaceful. It was molten and chaotic. Volcanoes raged. Asteroids pummeled its surface. Lightning split the skies, igniting the primordial atmosphere. And amid this violent ballet of natural forces, something remarkable began. Carbon compounds, ammonia, water vapor, methane, all dancing together in a planetary cauldron, began forming the building blocks of life. Organic molecules, the precursors to amino acids, the ingredients of proteins and DNA. Now, hold to that thought, because what scientists have just detected on WASP-39b, those same kinds of organic molecules, may represent an echo of what happened on Earth 4 billion years ago. Only this time, the stage is set light years away under an alien sky around a foreign star. But let's be clear, these organic molecules are not life. This is not a radio transmission from ET, nor is it proof of little green beings waving at us from a distant moon. No, this is something far more profound. It's the suggestion that the chemical steps leading toward life, the basic recipes, are not confined to Earth's special conditions. They're written into the universe itself, and if that's true, the story of life may not be ours alone. What makes this moment so transformative is that we didn't stumble upon these molecules by accident. This wasn't a random blip or a glitch in data. It was the result of decades of preparation, ingenuity, and precise collaboration. From the earliest dreams of space telescopes in the 1970s to the eventual launch of the JWST in 2021, scientists have been preparing for this very kind of analysis, where we don't just see distant planets, we taste their chemistry. Think about that. Until recently, exoplanets were only theories. Then, in the 1990s, we began confirming their existence, first through the wobble of stars, and later through their dimming transits. By the early 2000s, we had catalogued dozens. Today, that number exceeds 5,000 confirmed. Exoplanets, with thousands more waiting in the wings. But confirming a planet is one thing. Characterizing its atmosphere, that's a whole different frontier. The key lies in spectroscopy, a technique as beautiful as it is powerful. When light passes through a gas, specific wavelengths get absorbed by molecules. It's like a barcode. Each chemical has a unique signature. By spreading the light out into a spectrum, we can see these dark lines, these telltale fingerprints, and with the right instruments, we can decode them. But WASP-39b isn't just a random gas giant. Its atmosphere, swollen by its proximity to its star, acts almost like a lens, letting more starlight filter through, giving us a richer signal. And the JWST, it's built to see, in infrared, the very part of the spectrum where many molecules absorb light. This synergy, this cosmic alignment of science, technology, and target, was exactly what made the discovery possible. One of the most astonishing aspects of this analysis was how detailed the spectral data was. In past missions, we could detect broad features, water vapor, carbon dioxide, on the biggest and puffiest of planets. But now, with JWST, we're detecting not just categories of molecules, but specific organic compounds, some of which are delicate and reactive. The instruments on JWST are so sensitive, they can detect changes in brightness as tiny as 100 parts per million. That's like detecting the shadow of a fruit fly crossing in front of a floodlight from hundreds of trillions of kilometers away, and there's something else. This wasn't just one detection. It was 4 separate observations using multiple instruments, each confirming the presence of these molecules. In science, replication is everything. A one-off can be a fluke, but 4 times, from multiple angles, that's a signal. So what does this mean for the field of astrobiology? It means we're entering a new era, not just of exoplanet science, but of comparative planetology. Just like Charles Darwin compared the beaks of finches across the Galapagos Islands to understand evolution, scientists can now compare the chemical atmospheres of planets across the galaxy to understand the diversity and maybe the direction of chemical evolution. We can start asking deeper questions. What kinds of stars tend to have organic-rich planets? Do certain planetary masses or orbits encourage complex chemistry? How does radiation from a host star affect atmospheric stability? And here's where the mystery deepens. On Earth, the emergence of life required more than just organic molecules. It needed a stable environment, liquid water, protection from radiation, and probably millions of years of chemical trial and error. But if organic molecules are this common, even on planets that are blisteringly hot and bombarded by radiation, then perhaps the chemistry of life is a universal feature of planet formation. Perhaps planets are born not sterile but chemically rich, waiting for the right conditions to cross the threshold into biology. This line of thinking ties back to a principle known as the mediocrity principle, the idea that Earth is not special and that whatever happened here is likely to happen elsewhere. If methyl chloride and hydrogen cyanide are present on an overheated gas giant like WASP-39b, then the same processes might be occurring on rocky worlds in more temperate orbits. Planets like K2-18b, which has also shown hints of organic molecules, or LHS-1140b, a potentially Earth-like world orbiting a red dwarf star just 41 light-years away. And that brings us to an unsettling and exhilarating possibility. We might be standing at the dawn of a scientific revolution as big as the Copernican shift. First, we learned that Earth wasn't the center of the universe. Then we discovered that stars had planets. Now, we're discovering that those planets have chemistries that echo our own. The next step? Finding those elusive biosignatures, specific combinations of gases that strongly suggest life. But even without that, what we've seen in the skies of WASP-39b is enough to make us pause. It reminds us that the universe is not Static or silent, it's alive with process. Carbon cycling, molecular forging, radiation sculpting the skies of distant worlds. And through it all, humanity, tiny, fragile, and just beginning to understand, listens. Let's now dive into the heart of this discovery, the alien world known as WASP-39b. Just its name carries the cold precision of astronomical cataloging, but make no mistake, this world is anything but ordinary. Orbiting a star roughly 700 light-years away in the constellation Virgo, WASP-39b has become one of the most scrutinized planets in our galactic neighborhood. And not because it could support life as we know it, but because it offers a window into the chemistry of alien skies. WASP-39b is a gas giant, similar in size to Saturn, but its characteristics are wildly different from anything in our solar system. For starters, it orbits extremely close to its host star, so close, in fact, that a single year on WASP-39b lasts only 4 Earth days. This close orbit subjects the planet to relentless radiation, heating its atmosphere to around 800 degrees Celsius. That's over 1,400 degrees Fahrenheit. At such temperatures, no life form we know of could survive. And yet, that very extremity makes it a perfect laboratory. Imagine standing on a spacecraft hovering above its swirling atmosphere. Below you, thick clouds churn in exotic hues, saffron, violet and electric blue, colors not just for drama, but caused by chemical reactions unseen on Earth. Gases expand and rise violently, caught in winds that may reach thousands of kilometers per hour, driven by the intense stellar heating on one side and perpetual darkness on the other. It is in these alien winds, this ceaseless hurricane of superheated gas, that scientists detected something extraordinary. A suite of organic molecules, including sulfur dioxide, carbon monoxide, water vapor, carbon dioxide, and most intriguingly, methyl chloride. That last one is especially compelling. On Earth, methyl chloride is produced biologically, from ocean-dwelling plankton and industrial processes alike. Finding it on a gas giant raises new questions. Was it formed by purely chemical reactions in the atmosphere, or could there be more exotic processes at play, ones we don't yet understand? Let's take a closer look at the science behind this detection. The James Webb Space Telescope, JWST, used a technique called transmission spectroscopy. Here's how it works. When WASP-39b passes in front of its star, a fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. This light carries the signature of the gases it passed through, sort of like sunlight shining through stained glass. Certain molecules absorb specific wavelengths of light, leaving a fingerprint in the resulting spectrum. With this technique, JWST didn't just see the presence of a single compound, it detected multiple molecules across different spectral bands, using several instruments including NIRS-PEC and NIRCAM. This multi-instrument verification added tremendous confidence to the findings. The data showed not only the presence of carbon-bearing molecules, but also complex interactions between gases, chemical pathways that can lead toward prebiotic environments. And let's pause here to appreciate just how delicate this measurement was. The atmospheric signals that revealed these molecules were buried in the light of a star 700 light-years away. That's light that has been traveling since the time the Vikings were crossing the North Atlantic, arriving now through the vast corridors of space to whisper clues about a world we cannot touch. It's cosmic archaeology, except the relics we're uncovering are made of vapor, not stone. This is why WASP-39b is a treasure trove. Even though it's too hot for life, its bloated atmosphere, heated and expanded by stellar radiation, acts like a magnifying glass. The planet's puffiness gives us a deeper, more detailed look into its atmospheric chemistry than smaller, more temperate exoplanets allow. In this way, WASP-39b serves as a Rosetta Stone for planetary atmospheres. We can decode it now and use what we learn to better understand the fainter, more Earth-like signals we'll study in the future. Now, there's something else to consider: metallicity. That's a term astronomers use to describe how rich a star or planet is in elements heavier than hydrogen and helium. The JWST data showed that WASP-39b has an unexpectedly high level of metallicity in its atmosphere, particularly in its carbon-to-oxygen ratio. This kind of chemical fingerprint suggests that the planet may have formed far from its star, where more ices and carbon-based compounds were available, and then migrated inward over time. This idea, that planets migrate after they form, is relatively new in planetary science, and WASP-39b's chemistry supports it. It's like a chemical passport, stamped by the different zones of a planetary nursery. And if planets can migrate and bring their chemistry with them, then it means the ingredients for life can be stirred across vast distances of a solar system, or even between solar systems. The galactic mixing bowl is far more dynamic than we ever imagined, and this is where science and imagination collide. Because now we're not just detecting organic molecules, we're inferring histories, journeys, the life stories of planets. Imagine reading a novel where every character is a planet, and their chapters are written in carbon, oxygen, sulfur, and silicon. Every absorption line in that spectrum is a sentence from an alien biography. And some of those stories, just maybe, are going to include a chapter about life, but for that we'll need more than gas giants. We'll need to peer into the atmospheres of terrestrial planets, rocky worlds orbiting in the habitable zones of stars. That's the true next step. But make no mistake, discoveries like those on WASP-39b are the rehearsal, the first rehearsal for that grand performance. And so we arrive at a fascinating turning point. The instruments are ready, the universe is speaking, and humanity is learning to listen, not with ears, but with mathematics, mirrors, and the silent precision of light. And the more we listen, the more we find that alien skies are not so silent after all. Imagine a cosmic detective story where every clue is hidden in light, every answer is encrypted in chemistry, and every revelation brings us one step closer to understanding whether we are alone. That's precisely where we are now, at the thrilling edge between data and discovery. We've looked into the boiling skies of WASP-39b and seen whispers of chemistry that might hint at life's building blocks. But what happens next? What does this mean for the future of exoplanet exploration and the deeper search for extraterrestrial biology? To truly appreciate what comes next, we have to recognize the significance of this scientific threshold. For decades, our understanding of life's potential elsewhere in the universe has been limited by a simple truth. We couldn't study alien atmospheres in detail. Sure, we had clever models, and yes, we found thousands of exoplanets, but they were names and numbers on star charts. The James Webb Space Telescope, JWST, has changed that. It didn't just open a new window to the cosmos, it shattered the glass ceiling. For the first time in human history, we are performing atmospheric chemistry on worlds orbiting stars hundreds of light-years away. It's the birth of a new science, exo-atmospheric biosignature detection. That might sound like a mouthful, but it simply means we're now able to identify signs of potential life in the air of alien planets. And that's not science fiction anymore, it's happening now. But let's take a step back and ask, what actually counts as a biosignature? After all, we've detected molecules like water vapor, carbon dioxide, and even methane before. But those alone aren't definitive signs of life. That's because such molecules can be produced abiotically, meaning through non-living chemical reactions. On Venus, for example, we find sulfuric acid clouds. On Titan, Saturn's moon, we see methane lakes. Nature is a master chemist, and not every intriguing compound is a breadcrumb on the path to biology. So how do scientists distinguish between a chemical fingerprint that simply looks exotic and one that might actually point to life? The key lies in combinations. Certain mixtures of gases, when found together, don't make sense unless there's a biological process at work. Take Earth's atmosphere as a model. Oxygen, ozone, nitrogen, water vapor, and methane, these exist in a delicate balance that's maintained by living organisms. Without life, that balance would collapse within centuries. So when we look at other planets, we're not just hunting for a single molecule, we're searching for chemical disequilibrium, the sort of imbalance that suggests something is constantly regenerating certain gases. That's what makes the discovery on WAS P39b so compelling. It's not just that we found carbon dioxide and sulfur dioxide, it's how those gases interact, how they were distributed vertically in the atmosphere, and how they relate to ultraviolet light from the host star. All of this builds a narrative, a hypothesis about what's happening on a planet 700 light-years from Earth. But even with such a powerful telescope, there are limits. Gas giants like WASP-39b offer clarity because of their bloated atmospheres, but the real challenge, the holy grail of exoplanet science, is detecting biosignatures on rocky, Earth-like planets in the habitable zone. These are the Goldilocks worlds. Not too hot, not too cold, where liquid water could exist on the surface. That's where life, as we know it, is most likely to emerge, and we are already looking. The James Webb Space Telescope has begun examining such targets. One of the most anticipated is TRAPPIST-1e, a rocky planet orbiting a red dwarf star, just under 40 light-years away. That may sound far, but in cosmic terms, it's our next-door neighbor. The TRAPPIST-1 system contains 7 rocky planets, 3 of which are in the star's habitable zone. If we can detect a similar mix of organic molecules, especially ones like methyl chloride, nitrous oxide, or ammonia, on one of these Earth-sized worlds, we might have our first real evidence of alien biology. Now, let's imagine that scenario for a moment. Picture a distant world, bathed in the crimson light of a cool red sun. Its skies are thick with clouds, rain falls on alien oceans. Perhaps winds sweep across landscapes, shaped not by trees and rivers, but by processes we can't even fathom. In the air, a cocktail of gases, methane, oxygen, carbon dioxide, and something unexpected, something that doesn't belong. And in the labs back on Earth, as scientists run the data through model after model, one conclusion keeps surfacing. These gases don't add up unless life is part of the equation. And that's where the debate begins. Even with all our advances, science is cautious. We need more than a strange molecule. We need patterns, repetition, confirmation across multiple observations and instruments. The declaration of life beyond Earth will not come lightly. It will be the most carefully peer-reviewed, triple-checked, scrutinized announcement in the history of science. And that's a good thing. But already, theoretical biochemists are preparing. They're building models of alien metabolisms, imagining life that breathes different gases, that thrives in different pressures and temperatures. Some researchers even explore the idea of shadow biospheres, life that operates on principles completely unlike DNA and RNA. It's not just about finding Earth 2.0, it's about expanding our definition of life itself. That's the power of these new discoveries. They don't just push science forward, they reshape the questions we ask. Suddenly everything is on the table. Could silicon-based life exist in a methane-rich world? Could microbial mats thrive in the ammonia seas of a super-Earth? Might we detect photosynthesis by analyzing the subtle reflectance of alien forests? And here's a fascinating twist. We might not even recognize alien life if we found it. That's not a joke, it's a serious concern among astrobiologists. Our instruments are designed to look for Earth-like signatures, but what if alien biology evolved along a completely different path? Would we mistake it for geology or simply overlook it altogether? That's why scientists are not just relying on one approach. They're integrating data from atmospheric chemistry, planetary formation models, stellar radiation studies, and laboratory simulations here on Earth. They're even using machine learning to identify biosignature outliers, unexpected, patterns that might indicate something unusual and possibly alive. And so, standing on the shoulders of missions like WASP-39b, we're preparing for something even bigger. A future where discovering life is not a question of if, but when. Every spectral line, every molecule, every wobble in a distant star's light, it all adds up to a singular truth. The universe is more alive with possibility than we ever dared imagine. Now that we've ventured through the scorching winds of WASP-39b, deciphering alien atmospheres and uncovering clues in the chemical makeup of distant worlds, let's pause for a moment and consider the broader implications. What does this mean for us, for humanity's place in the cosmos? The search for life beyond Earth isn't just an academic pursuit, it's a quest that defines our future. Think back to the dawn of human civilization. When our ancestors first gazed up at the stars, they saw distant points of light, beautiful, unreachable, and indifferent to the struggles of life on Earth. Over millennia, our understanding of the universe grew, transforming these points of light into faraway suns, each with its own worlds, its own story. But for all the progress of our species, our great technological advances, our explorations, our missions to the Moon, Mars, and beyond, there's still one question that stands above all others. Are we alone? In a way, the search for life beyond Earth is more than just a scientific mission. It's a spiritual one. It's a question about our place in the grand tapestry of existence. Are we the only conscious beings in this vast, star-strewn universe? Or are we simply one thread among billions, each of us trying to understand the infinite? The discoveries we're discussing today aren't just reshaping the scientific community. They're forcing us to confront these profound questions in new ways. With each new exoplanet discovered, with each new atmosphere analyzed, with each molecule of methyl chloride or sulfur dioxide detected, we're inching closer to an answer that could change everything. But the road ahead isn't paved with certainty. It's filled with challenges, questions, and mysteries that we can't yet fully comprehend. For example, take the concept of biosignatures. We've mentioned how scientists search for chemical signs that life might be at work on distant planets. But we've also touched on the reality that what we're looking for may not resemble anything we expect. Alien life may not fit the narrow mold of life as we know it. It could exist in forms and environments we can't even begin to imagine. It's like trying to define a new color without a language to describe it. How do you even begin? But here's the beautiful thing. The unknown is where the magic happens. As we push the boundaries of space exploration, we aren't just discovering new planets. We're discovering new ways of thinking. Each new discovery challenges us to broaden our understanding of what life could be and how we define it. We're not just looking for life elsewhere. We're learning what it means to be human and to be part of something so much larger than ourselves. Think about it. For centuries, humanity has wondered whether we are alone. And now, with the incredible power of the James Webb Space Telescope and future missions like the Nancy Grace Roman Space Telescope, we are finally in a position to answer that question. We have the tools to detect the faintest trace of life across unimaginable distances. We have the potential to uncover the most profound truths about the universe and about ourselves. But let's also remember that this is just the beginning. WASP-39b, with its scorching atmosphere and alien chemistry, is not the final frontier. It's a stepping stone. The real treasure lies ahead, in the cooler, rocky planets of the habitable zone, where liquid water could flow and where conditions might just be right for life to take root. Planets like TRAPPIST-1e, Kepler-452b, and even Proxima Centauri b are the ones that will ultimately define our search for alien biology. And each new discovery adds a layer to the story we're telling about the cosmos. The science is evolving rapidly. And just as the world was once stunned by the first images of the distant galaxies captured by HST, we're now on the verge of seeing something even more remarkable: the first potential signs of alien life. It's an idea that's both awe-inspiring and humbling. Just imagine humanity for the first time reading the chemical signatures of an alien world, maybe even detecting the faintest signs of life itself. But we must also be cautious. There's a reason that when we discuss this possibility, we speak of it in terms of biosignatures and possible life. Science isn't about sensationalism. It's about precision and care. We need to approach every discovery with skepticism, testing and retesting our results. The truth will come, but it will come slowly, painstakingly, with attention to detail, and the unyielding curiosity that defines who we are as explorers. As we stand on the cusp of this new era of discovery, we can't help but wonder, what will humanity do with this knowledge? Will we become a civilization that reaches out to these distant stars, seeking connections with other life forms? Or will we be forever confined to our small corner of the galaxy, isolated and alone? The answers may lie in the stars, or perhaps in the journeys we're about to take to uncover them. This is why your support matters. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Let's continue this journey and unlock the secrets of the cosmos, one discovery at a time. And finally, as you ponder the infinite possibilities, here's one last question for you. If we find life beyond Earth, what will it mean for us as a species? Will it bring us closer together, or force us to reconsider everything we thought we knew about the universe? The truth may be waiting for us, out there in the depths of space, but only time will tell. Thank you for joining us on this extraordinary adventure. Don't forget to like, share, comment, and subscribe. The journey is just beginning, and we need you by our side as we explore the deepest mysteries of the cosmos. Keep your curiosity alive, and remember, out there, among the stars, is a universe of wonder, just waiting to be discovered.